13.3, tangent lines. We're going way back to last semester to get this party started. Do you remember average rate of change? Write it down in the space below. And if you're following along on the video, this is a good time to pause. You may even want to go and look up the average rate of change somewhere else if you don't remember it. Average rate of change. The average rate of change for a function always involved 2 points on the function. So say we had a point x, f of x, and some other point a, f of a. Then the average rate of change between those 2 points is the slope between those 2 points. So we would say that the average rate of change is f of x minus f of a over x minus a. Remember, slope is change in y over change in x. For f of x equal to 1/4 x squared, calculate the average rate of change between the point 0, 0 and the point 4, f of 4. Sketch the line passing through both points. A line passing through 2 points on a curve is called a blank line. Okay, well, first things first, let's begin by identifying the average rate of change, then we'll progress to the rest of the problem. We need to find out what f of 4 is. Well, given that we are dealing with 1/4 x squared, if we plug 4 into that, this looks like it's the point 4 comma 4. So that makes our task a little bit simpler. Average rate of change should be f of 4 minus f of 0 over 4 minus 0, which means we have 4 minus 0 over 4 minus 0, which looks like 1 to me. Now, we were told to sketch the line passing through both points. So we'll go ahead and get this into place. And I'm going to call that 4, call that also 4, negative 4. So we know we had a point there. We would also have a point here. And 0, 0 was the main point that we were looking at. So if we're drawing a line between 0, 0 and 4, 4, then that is the line passing through both points. Now, perhaps visually, this gives us a better hint at what goes into our blank. A line passing through 2 points on a curve in this fashion is called a secant line. What is the average rate of change between 2f of 2 and 4f of 4? Again, sketch the secant line through the points. So 2f of 2, we need to evaluate again. If we plug in 2, we square it, we get 4, 1/4 times 4. That gives us 1. And we already did that work for 4f of 4. So my m, again, it's f of 4 minus f of 2 over, this time it's 4 minus 2. So I get 4 minus 1 up top, 4 minus 2 down below. And that will give me 3 halves, or 1.5. So definitely a steeper slope this time. Again, sketch the secant lines through the points. So if we had 4, we now need to also pick up 2. And And the 0.21 was the one we were really interested in. So let's get that secant line drawn in. Okay, so we see quite a bit steeper, even with my squiggly drawing. 2 is a good bit closer to 4 than 0 was, so we see our line pulling up to get closer and closer as there's less difference between these 2 points. Okay, even better. Rather than picking the value 2, let's do this for some arbitrary value x. So what is the average rate of change between x, f of x, and 4, f of 4? Well, m would be, let's use f of x as our starting value this time because we don't know how it stacks up relative to 4. We'll do f of x minus f of 4 up top. We will have x minus 4 down below. And we can simplify this a little bit. We know that f of x is 1/4 x squared, and that f of 4 was 4. And we'll just leave x minus 4 as it is. I'm okay with that 1/4 up top. I think this is a reasonable final answer for right now. Okay, and the secant line for the case above. Let's take a look at that situation with some live action on Desmos, because there's actually a family of secant lines. There's a different secant line every time we pick a different value x. Desmos will let us do that with a slider. Here we go. Right, so I've got my function in place here. F of x equals 0.25x squared. I've also preset my point for f of 4. That's the point P on the graph for f of 4 right there. And then because it's Desmos and Desmos doesn't like reusing letters, my x f of x point I've had to label q. So q f of q is our arbitrary point, and we've used a slider to enable looking at different values of q so we can see what happens as q moves farther from 4 closer to 4. Now, when we start moving q around, let's go ahead and move q up to 2 as we just did. Okay, so that's where we see when we look at our slope equation, which I've plugged in down below, that yeah, we're getting m as 1.5. When we moved q back down to 0, that's where we had our slope of 1 as in our initial calculation. And what you see at the very bottom is a formula for the equation of the tangent line. Don't need to worry ourselves about that right now. I'm more interested in slope for this conversation. Now, as I get q closer and closer to 4 itself, you see that the slope is getting steeper. And then suddenly the line goes away altogether and the slope was undefined. Because if q was actually 4, I would have 0 down in the denominator. And we can't do that. We can't calculate a slope with 0 in the denominator like that. But as soon as we move past 4, the problem's resolved and we see a nice secant line again. And it gets steeper, it gets steeper, it gets steeper as we go on up. But the thing that's an interesting question mathematically is if we can't calculate the slope of the secant line right at 4, what is the value that's being approached? What is the value of the slope that's being approached? We can see that it's pretty close to something there. Maybe if I push this, oh yeah, 4.2. What's m? What is m close to when I'm at 4.2? And what about if I'm a little bit under? What about if I'm at 3.8? So it looks like m is approaching some value, but then of course, as with any worthwhile limit, when we actually get right on top of 4 itself, we can't evaluate it. So interesting things to look at further. Okay, how can you mathematically describe the idea of the x value of our arbitrary point getting closer and closer to 4? Well, I think I may have let the cat out of the bag. I think I already used the word when we were looking at it on Desmos. But this is simply the limit as x approaches 4 of whatever it was we were considering. Oh, wait, yeah, that was average rate of change. And this brings us to something we hinted at the last time we did average rate of change all those months ago, and that is instantaneous rate of change. Instantaneous rate of change is defined as the limit as x approaches a of the average rate of change, f of x minus f of a over x minus a. Finally, only took us a few months. Tangentially related. If the type of line we were dealing with on the first page was a secant line, what's a related type of line that only touches one point on a curve? Well, if you said tangent line, you're correct. And this is the definition. The tangent to a curve y equals f of x at the point a f of a is the line passing through the point with slope m equal to x minus a. Pardon me, with the slope m equal to the limit as x approaches a of f of x minus f of a over x minus a. Let's do it. We were close to it. Find the equation of the tangent line to the graph f of x equals 1/4 x squared at the point 4, 4. So first we need to find that slope. So the limit as x approaches 4 of 1/4 x squared minus 4 over x minus 4. Let's see how this works for us. I don't know if this one simplifies easily or not. Okay, so if we shuffle and combine, I've got a 1/4. I think I can pull my 1/4 out. Let's put a 1/4 on the front and make it x squared minus 1 over x minus 4. Okay, so even with that, this doesn't simplify. There's no nice, clean, easy algebraic way out of this. So we're going to have to do it numerically. So use a table. So let's start out with 3.9, 3.99. Let's not belabor this too much. Let's then use 4.01 and 4.1 as our other values here. And I'm going to kick back to Desmos. So when I got up to 3.9, I see a slope of 1.975. And if I push up to 4.1, I see a slope of 2.025. So 4.01, it's practically 2. And 3.99, it's, again, going to be practically 2. I'm not even going to, we can see where it's heading. This is hand wavy, and it's perfectly sufficient for what we're doing right now. So the limit that we're converging on here is to say that m equals 2. And with that in place, we can then use a point slope form of the equation of a line, y minus y1 equals m times x minus x1, to get the equation of the tangent line. So for that, we'll say y minus, well, our point in question was 4, 4. So y minus 4 equals 2 times x minus 4. And if you want to get it into y equals mx plus b, then we will have y equals 2x plus 4 as the equation of the tangent line.